Hello, welcome back to the Jerusalem Science Contest. This is now week 2, and today we'll be examining chapter 2 of your textbook entitled The Mathematics of Radioactive Decay. Actually, the chapter starts out with something that's a little unusual because it doesn't keep in the theme with everything else that's in the chapter, but because it's mathematical, I think it was inserted at this particular point. And it actually has to do with the way in which we can calculate those of you that have taken chemistry and are familiar with the fact that if we look at the periodic table, we get these sometimes very, very strange fractional masses, atomic masses for various elements. And the way this is arrived at is actually a kind of weighted method of finding out what the percentage of each element is in the environment, and then multiplying that by the mass of the atomic mass of that element. So for instance, as an example, there's one given in your book, but I'll give you a different one that I just calculated myself, which is the element bromine, which has an atomic mass of 79.904. And the way that's arrived at, bromine is almost a 50-50 mixture of two isotopes. One of them is bromine 79 and the other one is 81. So if you were just to look at this atomic mass here, 79.904, you might assume that the mass of bromine was actually 80, but it's not. It's really the average of these two elements. So in fact, bromine 79 actually has a mass of 78.918, and I could carry that to many more places. That will be in atomic mass units. This is bromine 79. And bromine 81 is 80.916, 2906. And if you multiply each one of these by its actual natural abundance, so it turns out it's not quite 50-50. It's 50.69% bromine 79. So to express that percentage as a decimal, that's 0.5069. And then since there are only two naturally occurring isotopes, the other one, bromine 81, is going to have to be the difference between this and 100. So that's going to be 49.31. Will be the natural percentage of that will be 49.31%. So if we multiply this number times 0.4931 and this number times 0.5069, and then sum both of those up, we're actually going to get 79. I'll leave you to do the math. I don't want to really take a lot of time with that, but you'll actually get 79.904. And there's another example given in your book. So that's really all I wanted to say about that, but you should know how to do that. So the rest of this chapter is pretty much concerned with the mathematics of radioactive decay. That first, as I said, that introductory section didn't have anything to do with that. But when we talk about decay, one thing that we should be aware of is that decay, when we talk about nuclear decay, it's isotropic, which means that the decay is occurring. If I had for instance, if I had a sphere, I don't actually have something spherical here that I could show you, but if I assume this little ball of tissue paper is a sphere, in fact, the radioactivity that's coming out of this is coming out in all directions. It's going up, and it's going this way. It's coming towards me. It's going away from me. It's coming down. So it's actually occurring in all directions. It could cause us some problems when we're trying to actually observe this, because we may not be counting every single decay that's actually occurring. So we have to take that into consideration, and we'll have more to say about that a little bit later in this lecture. So anyway, in terms of actually looking at decay, which is isotropic, we talk about the decay rate or activity. This is how fast decay is occurring. And decay occurs if we were to actually plot the amount, the number of radioactive atoms, the number of atoms that were actually decaying, or actually the number of atoms that we had that were radioactive. If we plotted that over time, so these are radioactive atoms, and this is time, what we would find is that this doesn't fall off in a linear fashion, but it falls off in a kind of curve that looks sort of like this. If we wanted to actually get a linear representation of this, what we would do is we would actually plot the count rate, which is the number of these atoms that are actually disintegrating over a period of time, and we would take that and plot that with respect to time, but we would use the logarithm of that. So we would take the log of the count rate, and then we would plot that over time. And when we did that, we would find that we got a nice straight line relationship. So that's what that's telling us when we see something, when we see a relationship like that. It's telling us that this relationship is actually exponential, or we could express it logarithmically. And what we say is that if we talk about the activity, we would say that the activity, we could have actually two. Let me erase this now. We'll say that if we've got a radioisotope that is starting to disintegrate, it's starting to decompose or convert into something else, some other element. What's happening is we'll start out at one time, and we'll say that this is its activity at the start, and then A2 will be its activity after some period of time. So this is activity to begin with. And we'll measure the activity in terms of decays per some unit time. So it might be decays per second. Sometimes I may use the word, it's often used interchangeably. Your book uses the word decays. Sometimes we'll use the word disintegrations, but it's the same thing, really. So the activity at the start in decays or disintegrations, usually it's probably going to be mostly per minute, disintegrations per minute. And this will be the activity after some time passes. We'll say a time, this is say T1, so this will be a time T2. But that's T1, after T2. So this is activity at some time later on. Then if we take the natural logarithm, that's the logarithm to the base E, where E is, E is one of these numbers that's kind of like pi. It's one of these infinitely repeating, not repeating, infinitely random. Well, it's not random either, but it's 2.718 something, and it's a whole bunch of digits after that, which I don't really know, but you can certainly enter E on your calculator and to be able to do these calculations. But it's the log, the natural log of A2 divided by A1. So if we take that ratio, that's going to be equal to minus KT. T is the time, and K is something that's called the decay constant. And it's going to have units that are going to be reciprocal time. So it might be something, it might be per second, second minus 1 or minute minus 1, whatever. It's going to be, it will have the units of reciprocal time. Now notice that this is negative. And the reason that it's negative is because A2 is always going to be smaller than A1, because these are disintegrating, so the activity is going to fall off with time. And if you take the natural log of a number that's less than 1, you're always going to get a negative number. So the two negative numbers are going to cancel out. You're not going to get a negative time. You'll actually wind up getting a positive time when you do these kinds of calculations. So this is the decay constant, K. And this isn't always the most useful way of expressing this. Another way that we can do it is, if we don't want to do it in the logarithmic form, we can write this out in the exponential form, and we can say that A2 equals A1 times E. There's our E to the minus KT. So that's just, both of these are equivalent expressions, It's just that one is written in the exponential form, the other one in the logarithmic form. But much more useful than that is the fact that we can also say that k is equal to the natural log of 2 divided by something called the half-life. Now the half-life, what the half-life is actually the amount of, you just write this as a subscript, pardon my sloppy handwriting, but it's T 1/2, and that's the half-life, and this is the amount of time that it takes for any given radioisotope, a certain amount of a radioisotope, for half of it to actually convert to another isotope or another element. So that particular amount of time is referred to as the half-life. So what this is telling me is that if I know the decay constant, which can be calculated, ln of 2 is approximately 0.693, memory serves me correctly, yes. And so we could actually say that this is equal to, k is going to be 0.693 divided by the half-life. And from that relationship, then we also know that the half-life is going to be 0.693 divided by k. So there's a number of things that we can do here. One of the more interesting things that we can do is we can actually rearrange this equation a little bit to get something that's a little bit more useful for us. And we can actually, if we actually substitute in a little bit with this expression here, we can come up with the fact that, for instance, if we're trying to find, and there's an example given in here, let's see, where you're asked to find a radionuclide, this is on page 19 of your text, has a half-life of 6.01 hours. If the activity is currently 5430 disintegrations per minute, what will the activity be 4 hours from now? So in order to do that, you want to use this equation. So you put in the value, what you're trying to solve for is A2, A sub 2. So A sub 1, which we're given the activity currently, which is 5,430 dpm, disintegrations per minute, and then we're going to raise that to e to the minus kt. Now we know that k is going to be the natural log of 2 divided by the half-life, and we're told that this element has a half-life of 6.01 hours. So this becomes, and you can see this on page 19, it's minus ln of 2 divided by 6.01 times the time period, which in this case is 4 hours. And if you actually apply that, the activity, current activity, times that e to the minus kt, you get a new answer of 3423 disintegrations per minute. So yeah, there's another example given in here where you're using this format here, and in this particular case, you're being asked to find the half-life, and it's a little bit easier to do it in this way. So if I know that a radionuclide has an activity of 1.38 times 10 to the 5th decays per minute 60 days ago, that was its activity. But now its activity is all the way down to 6.05 times 10 to the 4th decays per minute. What is its half-life? I just substitute it in with this equation. I'm going to erase this here. And I'm going to use this equation. But now I'm going to express this as ln of A2 over A1 is going to be equal to 0 minus 0.693 divided by the half-life of the element times the time period. So that's the other way of expressing this. And if we put this in, the actual values here, the half-life is 50, well, the half-life is what we're trying to calculate. So if we want to calculate that, what we have to do then is say that T1 half, let me put this over here, T1 half is going to be equal to ln, it's going to be equal to 0.693, I'm sorry. So we're going to bring this up here and we're going to divide by that. So T1/2 is going to be equal to minus 0.693 divided by ln of A2 over A1. So if we had then substituted the values for A2 and A1, 6.05 times 10 to the 4th, 1.38 times 10 to the 5th, disintegrations per minute, those units cancel out, and we're going to get an answer once we plug everything back in. We'll get an answer for the half-life of 50.4 days. So, you know, you have a way of actually using these equations then to calculate not only the half-life but the decay constant, if you want that, or if you the question was asked, what I know what the activity is now, what was its activity sometime in the past, or what will its activity be sometime in the future. I can do those kinds of calculations as well using that. Another example here is something that you should also know, that sometimes instead of using disintegrations per minute, we use other units. So when we're talking about radioactivity, there are a couple other units that are used. One unit, which is fairly large, is the Curie. We don't usually use the Curie, but we're more likely to use a millionth of a Curie, a microcurie. And one microcurie, 1 micro, that's a symbol for micro, curie of any radioactive substance is going to be equal to 2.22 times 10, times 10 to the 6th disintegrations per minute, decays per minute. So we can use that number. And using that number, that will enable us, for instance, if we're given microcuries, but we want to convert back into DPM, we can use this kind of relationship. 1 microcurie over 2.22 times 10 to the 6th DPM is equal to 1. Or the inverse of that is also true. The 2.22 times 10 to the 6th DPM over 1 microcurie is equal to 1. And then that becomes a conversion factor, and we can just convert from, if we're trying to go from DPM, if we've got DPM already and we wanted to go into microcuries, we would use this relationship. If we had microcuries and we wanted to go to DPM, we would use the inverse of that in order to find the DPM. So that's something else, and that's the example on the bottom of page 19. One other thing, I talked a little bit previously about the fact that since radioactivity is isotropic, that you've got decays going out in various ways, that frequently we're using detectors that are only going to pick up those decays that are heading right into the detector. So we're going to miss the ones that are going out to the side and going to the back and coming down and up. They're not going to necessarily be, they probably won't be picked up by the detector. So because of that, what we measure using the detector, what we call counts per minute, is not the same as decays per minute. If we had what we would call 100% efficiency, that is, if every decay gave us a count, we would then say that counts per minute and decays per minute were the same. But it turns out that for most detectors, that's not the case, and we're going to find that the efficiency for the detector is somewhat lower than that. And so what we're going to see is that the percent efficiency is nothing more than the number of counts per minute divided by the number of decays per minute. It's the percent efficiency. And we multiply that by 100. And so, for instance, if there actually were 40,000 decays and we were only picking up 4,000 counts, that would give us a 10% efficiency for our detector. So there's some examples of that as well, and that's easy to calculate. Another relationship that you should be aware of is the fact that activity. And by the way, there are a lot of equations in here, and I don't expect you to memorize all these equations. So for for the exam, I think what I'll do is I will actually include in there the pertinent equations that you'll need to solve. There won't probably be all that many math problems. If I give you 20 problems on this exam, maybe I'll limit the actual ones where you have to use a calculator. I would bring a calculator, definitely. I might limit that to 4 of the problems. So the other ones will be more conceptual in nature. Or they will be things that you can pretty much do in your head. As for instance, if I were to say to you that, as an example, let's say I've got a particular radioisotope and it has a half-life of 1 year, or so we'd say T1 half equals 1 year. And if I were to ask you how much of this, if I started out with 1 kilogram of it, and how much of it would be around in, let's say in 10 years, you would say, okay, so that is going to be, I'm going to lose 1/2 of this each year. After 10 years, I will have lost 1/2 to the 10th, which turns out to be, I think, 1/1000, and memory serves me correctly, 1024. So approximately, I would have about 1/1000th of that left, and that's going to give me, that's going to be about 1 gram. So just as an example, that's the kind of thing where you don't even really need a calculator. Well, you might need a calculator to find out what 2 to the 10th is. But this would be it's going to be 1/2 to the nth, where n will be the number of half-lives. So if I said 10 years, that would be 10 half-lives. But you know, I would give you, if I give you a problem that would be a simple problem like that, you know, I wouldn't even count that necessarily as one of the problems where you would need to use a calculator. That's a fairly simple kind of thing.